Hello, everybody. Welcome back. Today we're going to be looking at Unit 9.10, which is all about electrolysis and Faraday's law. So let's get started. So let's start off by talking about what electrolysis is in the first place. The process of electrolysis, or creating what's called an electrolytic cell, which is different from a galvanic or a voltaic cell. An electrolytic cell is run by running a galvanic cell backwards. Now, what do I mean by backwards? I mean that the electrons would be flowing in the opposite direction. Now, if you will recall, galvanic cells, when you connect everything properly the way it is and you have this redox reaction, it is a spontaneous process. Electrons will start to flow through that wire, through the voltmeter, on their own, spontaneously. Electrolytic cells, this is a non-spontaneous process. How do you get electrons to move through the wire in the direction that they would not move normally on their own? You have to force them through the wire in the opposite direction. So you have to force a current in order to get an electrolytic cell. This is, of course, again, a non-spontaneous process. Now, why would you do this? Why would you choose to run a galvanic cell backwards? Well, electrolysis is sometimes used for the processes of decomposition, but a lot of times it is used for a process called electroplating. And we're going to see some math and some useful applications of this a little bit later in this lesson. But if you will recall, from a previous subunit, when a galvanic cell runs, one of the metal electrodes is gaining mass over time as the galvanic cell runs, and the other electrode is losing mass. Well, what if we wanted it to be the other way? I mean, let's say, for example, a copper electrode is losing mass, and I don't know, I'm just making this up. An iron electrode is gaining mass. Well, if we wanted it to be the other way around and we wanted the copper electrode to gain mass, we wanted to get more copper metal, we would have to run the galvanic cell backwards. And that's not going to happen on its own, so you have to force it. So let's just kind of refresh our memories on all of the different parts of a galvanic cell. Okay, galvanic cells, of course, have an anode and a cathode. You have two metal electrodes that are immersed in aqueous solutions, and we've got electrons in this particular diagram flowing from left to right. That turquoise box in the middle is supposed to represent a voltmeter. Okay, now we're going to play a little game here. On the next slide, I have an electrolytic cell set up with the same substances, zinc and copper, but I want you to notice the differences. It's like one of those little games where you have the pictures side by side and you have to pick out the differences. Some of them will be immediately noticeable and others may be a little bit more subtle. So here we go. I'm going to flip back and forth between these two slides. So here we go. Here's our galvanic cell. Here's the electrolytic cell. Galvanic cell, electrolytic cell. There's multiple differences, some of which I said are very obvious, some of which are a little bit more subtle. I'm just going to do this a couple more times, and I want you to notice the differences. Okay, so Probably the most immediate difference you may have noticed is that between the galvanic cell, where we have the voltmeter up at the top, that's not what is there in an electrolytic cell. We have to have a battery. And ladies and gentlemen, you need a power source for an electrolytic cell because, as we said, moving electrons through the wire in the opposite direction is not a process that's going to happen on its own. It has to be forced. So we need a battery or some kind of power source. And if you'll notice, if this redox reaction is going to register a voltage of 1.10 volts, our power source using the same redox reaction has to be providing at least greater than 1.10 volts. It's got to be able to overcome that potential. Okay, so along the same lines, this one was a little bit more subtle. Look at the arrows for the direction that the electrons are flowing. In the galvanic cell, they're flowing from the zinc half cell to the copper half cell. In this one, they're flowing from the copper to the zinc. So the direction of flow of electrons is changed. Another thing you may have noticed, there are not two separate chambers in the electrolytic cell. This galvanic cell has two separate half cells. The electrolytic cell, everything is floating in one big beaker. Okay. And by the way, shame on me for not including my salt bridge here, but we definitely don't have a salt bridge here. That's another thing that should pop up. And then the final difference, look at the words anode and cathode. Okay. Zinc is still on the left-hand side. Copper is still on the right, but the position, excuse me, of anode and cathode have flip-flopped. Okay. Now, let me say something to you. Let me say two things to you, actually. No matter if it's a galvanic cell or an electrolytic cell, oxidation will always take place at the anode. Reduction will always take place at the cathode. Now, since those reactions have been sort of flipped around, the designations of anode and cathode from this cell to this one have changed, because where I was having oxidation take place on the zinc side, now oxidation is taking place at the copper side. The second thing I want to say to you guys, no matter if it's a galvanic cell or an electrolytic cell, electrons always flow from anode to cathode, no matter what. Doesn't matter if it is a galvanic cell or electrolytic cell. Electrons always flow from the anode towards the cathode. Okay. So let's just kind of bring this together. What are some of the differences? All right. A galvanic cell, of course, has a thermodynamically favored reaction, whereas an electrolytic cell is thermodynamically unfavorable. In a galvanic cell, your anode and cathode are in separate chambers, separate half cells, whereas in an electrolytic cell, they're usually all in the same chamber, all in the same beaker. A galvanic cell needs a salt bridge, and shame on me for not drawing that into that diagram earlier. An electrolytic cell doesn't need a salt bridge because everything's all in the same compartment. An electrolytic cell needs a power source, like a battery, or to be plugged into the wall. Okay, and a galvanic cell does not. And mathematically, a galvanic cell is going to result in positive cell potentials, positive voltages, whereas electrolytic cells are going to result in negative cell potentials. Okay, but what do they have in common? We talked about this. Oxidation is still taking place at the anode. Reduction is still taking place at the cathode. It's just that the The locations of anode and cathode may have flip-flopped, and electrons will still flow from anode to cathode, and ion flow will still be cations are flowing to the cathode, anions are flowing to the anode. Okay. So I'm going to have you pause your video and try this one on your own. Okay, but let me just kind of introduce it to you. All right, we've got it tells us that water is being electrolyzed. Electrolyzed means electrolysis. Okay, and they've got a diagram at the right. I've given you a little table that has the two half reactions that are involved. And you are to come up with the balanced equation, the standard cell potential, and then letters C and D ask you some questions about this electrolytic cell. Let me help you get started, just giving you a little bit of a hint. Remember, since this is electrolysis, the total cell potential is going to be negative. Okay, let that be your guide to help you determine that balanced equation. So pause the video and see how you do with this. Okay, let's check through these answers. Okay, so the first thing we were asked to do was to write the balanced equation for this reaction. And remember, the hint that I gave you was to remember that in an electrolytic cell, the total cell potential must be negative. So I know that that is the half reaction I'm going to have to flip. Remember, when you flip a half reaction, the cell potential becomes, or it changes sign. And again, just like in a galvanic cell, the half reaction that you flip is the reason you flip it is because you need an oxidation half reaction. Just like in a galvanic cell, guys, that half reaction is the anode. So let's look at what happens when we use these two half reactions. And so I wrote them out, and you can see that in order to equalize the number of electrons, I multiplied that second half reaction, I multiplied it times 2. My electrons then canceled out, and I wrote everything that is left. Now, this is not quite finished, and this is something that we sort of touched on in the acid-base unit. If you will look at these two things right here, we have 4 H pluses and 4 OH minuses. If those things are being added together, what does that create? It actually creates, let me write it out here, 4 water molecules. Okay, H plus and OH minus put together, that makes water, and there were 4 of each. Okay, and I can actually simplify this equation down even further because I can cancel out some of these waters. I can get rid of all 4 of those, and that leaves me with 2. So let me rewrite this. So there we go. Okay. For part B, all I have to do is add those potentials together, negative 0.70, negative 0.83, and that gives us negative 1.53. And it's negative. It should be. Electrolytic cells have negative cell potentials. And I want you to think about something for a moment. What sort of delta G Gibbs free energy value? What would that give us? And I'm not actually going to work through the math, but oops, sorry, let me bring that back up. Think about this equation. If this cell potential is negative, that is going to give us a positive delta G. Let's refresh our memories on what that means. A positive delta G means an unfavorable process, and that is correct when it comes to electrolysis. Okay. Part C says, is hydrogen gas produced at the anode or the cathode? Okay, remember guys, the designations are the same. Anode is wherever oxidation is taking place. Cathode is wherever reduction is taking place. So hydrogen is produced at the cathode because electrons are flowing into the side, the electrode, where hydrogen bubbles are appearing. Remember, guys, electrons still flow from anode to cathode. And in that drawing on the right-hand side, I can see that the electrons are flowing to the hydrogen compartment. Electrons are consumed in reduction. That's where reduction takes place at the cathode. So the hydrogen gas is produced at the cathode. And then the last part of this free response question says, explain why the level of liquid below the hydrogen bubble is lower than the level of liquid below the oxygen bubble. And before I pull up the answer, let me just refresh your memory on what our final equation looked like. Final balanced reaction. Look at the coefficients. Oxygen and hydrogen are being produced in a 1:2 ratio. So the balanced equation shows that twice as much hydrogen as oxygen is produced. Thus, there are more molecules of hydrogen than oxygen and thus occupy more space. There is twice as much hydrogen as oxygen. Okay. Now, the final thing that you might be asked to calculate is what's called the stoichiometry of electrolysis. And let me remind you again, electrolysis is a process that is very often used for something called electroplating. Okay, for example, I'm going to show you in a example problem in just a moment where, let's say you had an antique silver spoon, and you wanted to coat that spoon in gold. Okay, we can calculate what kind of electrolytic cell is required, what kind of current, how long do I have to run it in order to coat that spoon. So to calculate the mass of metal that will be plated, okay, we're going to be talking about current and time. We're going to talk about charge. We're going to see that Faraday's constant again. Okay, and that's going to be able to tell us how many grams of this metal will electroplate out. So I'm going to show you an example. Okay, this question says, determine the mass of chromium that can be produced when a solution of chromium 2 nitrate is electrolyzed for 1 hour with a current of 15, and that capital A, guys, that stands for amps, okay, amperes. And those of you that are in physics, you may already know this. There's another way to write the unit of amps. 1 amp is the same thing as a coulomb per second. Now, what is a coulomb? A coulomb is just a unit of charge, okay, of electric charge. So what this is saying is that in this electrolytic cell, we are, quote, pushing, you can kind of think of it that way, forcing 15 coulombs of charge through the wire every second. Okay, fine. Well, how long are we running this cell? We're running it for 1 hour, which is 3,600 seconds. if I multiply these two values, the seconds will cancel out. And let me pull up my calculator here. So 3,600 times 15 gives me this number. 54,000 coulombs. Remember, a coulomb is just a unit of charge. So over the course of 1 hour, we will force 54,000 coulombs through this wire. And from here, we can use dimensional analysis. So watch. At this point, I'm in coulombs. If you look, ladies and gentlemen, on your equation sheet where you are given Faraday's constant, you don't have to memorize it, it's there. Look not just at the number, but look at the units. Faraday's constant has units of coulombs per mole of electrons. So if I'm starting in coulombs right here, I want coulombs to cancel out. Watch what I can do. Faraday's constant is 96,485 coulombs per 1 mole of electron. And now coulombs will cancel out. Okay, I'm going to put moles of electrons here. And now I can get to, watch, moles of the metal that we are talking about. Okay, now, how do you know what numbers to put where? Okay, well, where is this metal coming from? It's coming from a solution where the ions floating around have a charge of +2. And we're going to turn those ions into the atom form, the metal solid form of chromium. Let's fill in the blank. What's going to go there? To balance this half reaction out, 2 electrons. For every 1 mole of chromium created, 2 moles of electrons will be pushed through the wire. And now moles of electrons will cancel out. Can you see now how I'm going to get to grams of chromium? Now it's just the molar mass off the periodic table. Okay, and so when I run this, do all of my calculating here, multiply all the numbers across the top and divide by the numbers on the bottom. And let's see, I'm going to round to 2 significant figures. I get this. Final answer. So if I wanted to plate a hubcap with chromium so it's beautiful and nice and shiny, I could take that hubcap, submerge it in a solution of chromium nitrate, force a current of 15 amps and run it for 1 hour, and that would deposit or electroplate 15 grams of chromium on that hubcap. Okay, so it's all just a matter of following the units. Okay, but I am going to show you a little bit of a shortcut. I didn't want to show you the shortcut first because I wanted you to understand the math first. But I have a little shortcut. All right, and here's the thing. You can calculate the mass of metal deposited. That would be this mass right here, with what I call the ATM fee equation, the little shortcut, okay? Whenever you go to, I want you to imagine that you are out somewhere and you need cash. And so you take your ATM card and you go to the ATM. And let's say you are a Wells Fargo bank customer, and the only ATM you can find is a Bank of America ATM. Well, if you go to an ATM that is not with your bank, typically you're going to have to pay some kind of a fee to use their ATM. So this is the ATM fee shortcut. Now watch how genius this is. And this is not my creation, by the way. I stole this from a colleague. The A stands for amperage, the current. So 15 amps. T of ATM stands for time. Just be careful, guys. It must be put in units of seconds. The capital M of ATM, that is the molar mass of the metal we're talking about. And then on the bottom, F of phi, that is Faraday's constant. Coulombs per mole of electrons. And the little e on the bottom, that is the number of electrons in that half reaction. And if you remember, that was a 2. Okay, and if you don't believe me, if you do 15 times 3600 times 15 divided by Faraday's constant divided by 2 and round to 2 significant figures, we will get that same answer again. It's just a little shortcut. And the reason that I really like this is because, ladies and gentlemen, sometimes in these electrolysis problems, they are not always going to ask you to solve for the mass of metal that was plated. Maybe they ask you to solve for the time. How long has this cell run if so many grams of chromium was plated? Okay, or they ask you to solve for the current. They can ask you any of these unknowns. Okay, so I think this shortcut is really, really handy to use. So I want you guys to try this one. You can use ATM phi if you want, or you can go just using dimensional analysis, your choice. But I want you to pause the video and try this one. All right, let's see how you did. I chose to use that little ATM phi shortcut equation, but even if you use dimensional analysis, we should get the same answer. So I plugged in all of my given information. The only piece I was missing was the time. Okay. And I've also just tried to draw your attention to how did I know what that the number of moles of electrons would be. Remember, guys, that comes from when you think about the half reaction. This gold right here in the solution is gold with a +3 charge. And what is it becoming? It's turning into solid gold. What completes that half reaction is 3 moles of electrons. We do the math. We solve for T, it comes out to 230 seconds. Remember, time in this ATM phi equation in these electrolysis calculations need to be in seconds. Okay? So feel free to use that ATM phi equation. I think it's great. Okay, now the last thing that I want to mention, on your equation sheet in the thermodynamics/electrochemistry section, you will find an equation that looks like this. Okay, I is current, amps. That little Q there is charge, okay, in coulombs, and T is time. And this is called Faraday's law. This equation basically just sort of sums up an electrolytic cell. Okay, the amount of charge that flows through an electrolytic cell is really just a factor of the current and the time that it's running. Okay, that's what that relationship is. And if you think about it, you know, if you use this little shortcut equation, Faraday's law, I equals Q over T, is really just a rearrangement of that, okay? Because I is amps, Q is coulombs, and if you multiply Faraday's constant times your mole of electrons times the mass of metal deposited divided by the molar mass, if you don't believe me, I promise you can see it for yourself. The unit that works out when you multiply all of that and divide by the molar mass, you will come out with coulombs. And T is time on the bottom. So Faraday's law here is really just this shortcut equation rearranged. Okay, so I just wanted you to be aware of what this equation is. I don't imagine you will use it too often, though. And the last thing I want to say is that on a very rare occasion, you will see questions that give you a unit of a Faraday, okay? Meaning that is a unit. And it's not written on your equation sheet, so I wanted you all to be aware of what a Faraday is, okay? The unit of a Faraday, 1 Faraday is equal to 1 mole of electrons, quote, pushed through the wire. I say pushed because electrolytic cells are not favored. Okay, so I want you to look at this question here and we'll work it together. Remember, multiple choice questions can be done without a calculator. It says, in the electroplating of nickel, 0.2 Faraday of electrical charge is passed through a solution of nickel sulfate. What mass of nickel is deposited? Okay, we can use dimensional analysis for this one. It's actually easier than using some sort of shortcut. 0.2 Faradays, let me write that another way. 0.2 moles of electrons, because that's what a Faraday is. And from there, okay, let's think about our units. Moles of electrons. Moles of electrons, I can get to moles of nickel. Okay, now what goes where? Remember, think about the half reaction. Nickel is coming from a +2 charge, and we're going to be creating nickel metal. So what would fill in the blank there? 2 moles of electrons. So for every 1 mole of nickel, 2 moles of electrons will be pushed through the wire. Moles of electrons can now cancel. And now I can get to grams, which is what they're asking us. And the molar mass of nickel is 58.7. Okay, so this can be done without a calculator, ladies and gentlemen. Take it piece by piece. What is 0.2 divided by 2? Well, that would be 0.1. 0.1 times 58.7 is 5.87. So B is my answer. Okay, I just wanted to show that to you in case you ever see a question where you're given something having to do with electrolysis and your given information is in units of Faradays. So that wraps up Unit 9, and guess what? That is the very last subunit in the AP Chemistry curriculum. So this is the last video in my series. So I want to wish you the best of luck if you are taking the AP exam soon. You're going to do great. And I want to thank you for coming along with me on this journey and watching my videos. I have honestly really enjoyed making them. And I also want to wish you luck in whatever future endeavors come your way. So see you later.